Chapter 11, Intermolecular Forces, Liquids and Solids. In this chapter, we'll take a look at what causes the change in states of matter from gas to liquid to solid. And you should know some characteristics of each of these. Gases, totally disordered, much empty space. Particles are very spread out and have lots of freedom of motion. Liquids, disordered. There are clusters of free particles, and then crystalline solids, of course, very ordered arrangement, and they're essentially in fixed positions. Because the solid and liquid states of particles are closer together, we refer to them as the condensed phases, because the particles are much closer together than in the gaseous phase. The state a substance is in at a particular temperature and pressure depends on two antagonistic entities. The first is the kinetic energy of the particles, which is directly proportional to the temperature. And therefore, temperature and kinetic energy we kind of refer to as essentially the same. But kinetic energy, of course, has to do with the velocity or the speed of the particles. And the second is the strength of the attraction between the particles. And this will be essentially most of our focus throughout this entire chapter. What kinds of attraction are there between the particles of a substance in its gaseous, liquid, and crystalline state? We don't look so much at the chemical changes that they undergo in this chapter. We look more at the physical changes that particles undergo between the phases of matters of solid, liquids, and gas. And here are some more characteristics of those properties that you should know as well. Gases, liquids, and solids, read those over and memorize those because you should know the differences between them. So in this chapter, essentially what we'll be looking at is what are called intermolecular forces. Now, just to back up a second before we get deep into those forces, there's a difference between, and it's only a two-letter difference, between intermolecular and intramolecular forces. So let's review and let's take a look at the difference between the two because sometimes it's very confusing. Intramolecular forces are things that we learned in Chapter 8 and Chapter 9. These are things that connect inside of a molecule or a particle. They're like an intranet. We have an intranet inside of School District 194 that connects one building to the other and shares information across computers. It does not look and go globally. It's only inside of that organization. For example, in a water molecule, the intramolecular forces are the polar covalent bonds that hold hydrogens and oxygen together. The polar covalent bond would be referred to as an intramolecular force. Okay? Ionic bonds would be another example. They're inside of the molecule. Conversely, the thing that we're going to look at almost exclusively in this chapter are intermolecular forces. Those are like the internet. Those connect the entire world or connect country to country or, a computer from here to one in Thailand. These connections occur between particles. For example, here is a water molecule. Notice it's polar, negative end here, positive end here, connected to another water molecule. This dashed line right here is an intermolecular force holding one water molecule to another. Those intermolecular forces are what we're going to focus on in this chapter. The attractions between molecules are not nearly as strong as the intramolecular forces that hold compounds together. So the H to Cl bond right here, this polar covalent bond right here, is way stronger than the connection between one HCl molecule and another HCl molecule right here. These intermolecular forces are much weaker, but they have a significant effect on the physical properties such as boiling points, melting points, vapor pressures, and viscosities. Therefore, what phases of matter something is. So the intermolecular forces have big effects even though they're not as strong as things like covalent bonds. The group of these intermolecular forces are called van der Waals forces. And there's 4 of them that we'll actually look at in this chapter. 3 of them are called dipole-dipole interactions, hydrogen bonding, and London dispersion forces. And we'll look at each one individually here in just a second. The fourth type of intermolecular force is called an ion-dipole interaction. Ion-dipole interactions are important forces in solutions of ions, and the strength of these forces are what make it possible for ionic substances to dissolve in polar solvents. So, for example, let's say these are particles right here that are dissolving in something, and you can see right here that there's an attraction between the positive dissolved thing and the negative end of the other dissolved thing. These red dashed lines right here are the ion dipole attraction. Notice this particle right here has a dipole. Remember, dipole means two poles, one here and one here. And this is attracted to an ion, a charged particle right here, causing it to dissolve. Here's another example right here. These dashed lines are the ion dipole attraction. Of course, water is a really good solvent because of this. Water is a dipole substance, a polar substance, and it can attract to positive and negatively charged things. Molecules that have permanent dipoles are attracted to each other. You can see right here that there are these attractions between positive and negative things right here. And the positive positives, of course, repel one another. Negative and negative repel one another, but these positive negatives attract to each other. The positive end of one is attracted to the negative end of the other, and vice versa. These forces are only important when the molecules are close to each other. In other words, if they're in the gaseous phase, it usually doesn't make any difference. But if they're in the liquid or solid phase, they become very, very important. Now let's take a look at those three other types of intermolecular forces. We looked at ion-dipole. Now we're going to come back to those three that we had listed before. Dipole-dipole interaction, hydrogen bonding, and then ones that are called dispersion forces. So here's dipole-dipole forces. The more polar the molecule, the higher its boiling point. And if we look right up here, here are a number of polar molecules. Okay, remember a molecule is polar if it is asymmetrical. Okay, and you can notice right here that they have similar molecular weights, but you can see that the dipole moment increases right here, and therefore its boiling point increases. In other words, they stick together better the more polar the molecule is. London dispersion forces. Well, the electron of the 1s orbital of helium would repel one another and therefore tend to stay away from each other. It does happen that they occasionally wind up on the same side of the atom. Notice how both electrons ended up right here per chance at one time. This causes, at that instant, the helium atom to be slightly polar, with an excess of electrons on the left side and a shortage of electrons on one side. And that's illustrated, remember, by this little Greek letter delta and the minus sign right here because there's two electrons right here, and this little Greek letter delta positive right here because there's no electrons on this side. If there is another helium atom nearby, then it would have a dipole induced in it, as the electrons on the left side of the helium atom would repel the electrons in the cloud in helium atom 1, and then we would have this little attraction between the negative end where the electrons are and this positive one where the electrons are not. This attraction right here is known as a London dispersion, or simply a dispersion force. London dispersion forces, or sometimes just called dispersion forces, are attractions between an instantaneous dipole and an induced dipole. These forces are present in all molecules, whether they are polar or nonpolar. Notice a helium atom, of course, is not a polar substance because it doesn't have, it is symmetrical, but it can become asymmetrical at one instant, of course, if the electrons end up on one side. And so it's what's called an induced dipole, and therefore it's attracted to another one by this induced dipole attraction known as a London dispersion force. The tendency of an electron cloud to distort in this way is called its polarizability. And of course, if you have more electrons, you have more chance for it to possibly end up polarized, and therefore it has more London dispersion forces. So what are the factors that affect London dispersion forces? First of all, the shape of the molecule affects the strength of the dispersion forces. Long, skinny molecules, like N-pentane right here, tend to have stronger dispersion forces than short, fat ones. Okay, you can see this chubby one right here doesn't have nearly the surface area of this one. Since it has more surface area, more opportunity for instantaneous polarization. This is due to the increased surface area of N-pentane. You can see right here, increased surface area, more chances for those electrons to end up in one spot. Whereas here, since it's all kind of in a ball, less surface area. Another factor that affects London dispersion forces is a substance's molecular weight. If something has more molecular weight, it has more electrons, and therefore it has more chance for instantaneous polarization. Larger atoms have larger electrons clouds, which are a little bit easier to polarize. So which has a greater effect, the dipole-dipole interaction between two polar molecules or the dispersion forces that just happen instantaneously between two molecules, whether they're polar or not? If two molecules are comparable size and shape, the dipole-dipole interactions will likely be the dominating force. If one molecule is much larger than the other, then the dispersion forces will likely determine the physical properties. Okay, so the bigger it is, the more electrons it has, the more chance it has to be instantaneously polarized. So here is the third type of intermolecular force, and it starts with a question. Before we explain what it is, let's take a look at this graph. Notice how H2S, H2SE, and H2TE increase because the molecular weight of the substance increases. S, SE, and TE are all in the same family or same group on the periodic table. But you'll notice there's an anomaly. Normally you'd think that it would just go up kind of like a line like this, like the blue one does, where C, Si, Ge, and Sn all in the same group or family just generally increase, kind of linearly. But these guys, all of a sudden there's a jump. Even though H2O, oxygen, being in the same family of sulfur, selenium, and tellurium, H2O all of a sudden jumps way up here for its boiling point. Why, even though this has the lowest molecular weight, does H2O have such a high boiling point versus these other ones right here? Well, the polar series follows the trend from H2TE through H2S, going from right to left. But water is quite the anomaly. You can see it follows the trend, and then all of a sudden it breaks the trend right here. Why is that? Well, we explain it by a third type of intermolecular force that's actually a special case of dipole-dipole interaction called hydrogen bonding. This dipole-dipole interaction is experienced when hydrogen is attached to nitrogen, oxygen, or fluorine. I like to read it backwards. F-O or N spells phone, F-O-N. So if a hydrogen is attached to an F, an O, or an N, then all of a sudden that molecule can have what are called hydrogen bonds with another similar molecule. Notice here's an illustration of the hydrogen bond. H right here, which has a dipole, of course, because hydrogen's electrons are attracted to the oxygen. So it's positive right here, is attracted to the negative end of the oxygen right here. These three dots right here illustrate how they're connected. Same thing right here between two ammonias. Same thing right here between the ammonia and the water. Same thing right here between the ammonia and the water again. Hydrogen bonding arises in part from the high electronegativity of the nitrogen, oxygen, and fluorine. And if you remember back to our trends chapter, chapter 7, you'll remember that nitrogen, oxygen, and fluorine are the most electronegative atoms on the periodic table. And you can see right here, this is crystalline water right here, water in the solid phase. And you can see right here, here's the hydrogen bond, oxygen to hydrogen right here of another water molecule. And you can see that the water right here actually forms a really nice crystalline lattice that's kind of a hexagon in shape. And this actually is a lot more explaining right here than what this chapter is supposed to do. But you can see that there's actually lots of gaps or spaces right here where there's a lot of nothing, which causes water in the solid phase actually to be less dense than water in the liquid phase, which is very, very unusual. Not many substances do that at all. Also, when hydrogen is bonded to one of these very electronegative elements, the hydrogen nucleus is exposed. And remember, the hydrogen atom itself only has one electron. So if its electron is attracted to something else very strongly, that means its nucleus, which is simply a proton, is now exposed and can go do lots of strong attracting. That's why hydrogen bonding is so significant. So let's summarize the intermolecular forces. Remember, we said that there were 4 of them, 4 different types of intermolecular forces, okay? First of all, there were the dispersion forces right here that happens in everything. That's where the electrons all of a sudden are stuck on one side of the atom, and then they're attracted to an induced dipole in another one. Those happen between everything. They give a couple of nonpolar examples right here, but they happen in everything. Second are dipole-dipole forces right here. Dipole-dipole forces. Okay, those are ones where you have a polar molecule like H2S attracted to an H2S. Okay, and then thirdly, if we have a hydrogen attached to an N, O, or F, F-O-N, remember phone right here, then we have something called hydrogen bonding that we just got done explaining. Okay, we notice water, ammonia, hydrogen fluoride right here. And those are the strongest, actually, of the 3 types of intermolecular forces that are termed van der Waals forces, as long as they're of similar molecular weight to everything else. And then the 4th type of intermolecular force that we talked about way at the beginning was called an ion dipole force, and that would be where, like, water attracts to an ion. Water attracts to an ion, like when potassium bromide dissolves. And then lastly, this is not an intermolecular force, but an intramolecular force that's actually confused many times, is with something that's ionically bonded, like a metal and a nonmetal right here, or 2 polyatomic ions stuck together. The thing that holds those together are an intramolecular force between Na and Cl. And the reason they put this one in here is because a lot of people get confused by that and lump it into these 4 right here, which are intermolecular forces. This is an intramolecular force right here. So how do these intermolecular forces affect physical properties? How do these intermolecular forces affect the many different physical properties? First of all, the strength of attraction between particles can greatly affect the properties of substance or solution. One example right here is, notice how there's an attraction between these particles at the surface of a liquid and down into the liquid. But notice there's no attraction in the upward direction because there are no particles up there. But notice a substance right here, or a particle that's inside the liquid, is attracted to all the particles around it right here. Notice there's a difference right there. We're going to talk about how this is a separate type of situation right here because it's at the surface of the liquid. First physical property is viscosity. Viscosity is the resistance of a liquid to flow. It's related to the ease at which molecules can move past each other, and viscosity increases with stronger intermolecular forces and decreases with higher temperature. So when you heat it up, of course, it flows a little bit easier. You can see right here are some examples. Notice the molecular weight goes up, and therefore the viscosity goes up because the intermolecular forces are stronger. And you can actually test viscosity just by flowing something through a funnel like this. Faster it flows, the less its viscosity. Slower it flows, the more its viscosity. Second type of consequence of intermolecular forces are something called surface tension, and this is the one I alluded to with this picture just a second ago. Surface tension results from the net inward force experienced by the molecules in the surface of a liquid. Notice here something's just attracted to the side and down, and here you'll notice that something's just attracted in every single direction. And because of this, this surface right here forms what's called like a skin, or a kind of a strong surface tensed together, which allows things like bugs to walk on or float on top of water. And actually, it's because these molecules of water right here are attracting to the side and down. Okay, we'll do a couple of demonstrations with this in class as well that actually show you how the surface sticks together better than the interior of it, because it's attracted to the side down. So it lets you, allows you to float like a paperclip on top of water, even though the paperclip is more dense than water. Third thing that intermolecular forces very, very strongly affect are phase changes. And you should memorize what each one of these phase changes is called: vaporization, condensation, melting, freezing, sublimation, and deposition. Notice deposition is where you go from a gas to a solid. Memorize each one of these phase change names and know what they do. Notice energy is on the vertical side of this graph, and you notice you need a lot more energy to go from a solid to a gas than you do simply to go from a solid to a liquid. Okay? So what energy changes are associated with change of state? They're given special names, special fancy names for you to memorize. Okay? First one is called the heat of fusion. This is the energy required to change a solid at its melting point to a liquid. So we're going from a solid to a liquid. In past years, or in times past, they gave this heat of fusion a fancy name. They called it the latent heat of fusion. The word latent actually means hidden, and so they called it the hidden heat of fusion because you could heat up these solids, and then all of a sudden they'd start to be at the temperature where they would melt. For example, 0 degrees Celsius for water, but it would continue to stay in the solid phase, and people would wonder, well, why does it stay in the solid phase for so long if it's at 0 degrees Celsius? I thought it would melt instantaneously when it got there. Actually, you had to add a little bit more heat to make it change from the solid to the liquid. And this heat was kind of hidden, and so they called it the hidden heat of fusion or the latent heat of fusion, because you had to add a little bit more heat to make it change from a solid to a liquid. And you can see right here that the heat of fusion right here for water is 6 kilojoules per mole. You'd have to add that 6 kilojoules of heat at the exact 0 degrees Celsius, which is normally the melting point of water, to get it to go from the solid to the liquid. And conversely, you'd have to take away 6 kilojoules of energy to go from the liquid to the solid. Second one is called the heat of vaporization. This is the energy required to change a liquid at its boiling point to a gas. So you could have water, which at sea level boils at 100 degrees Celsius. You would get water to 100 degrees Celsius at sea level, but it wouldn't boil yet, because you would have to add another 41 kilojoules per mole right here to get it to go from the liquid to the gas phase. This was known as the latent heat of vaporization. The word latent, once again, is hidden because it's the hidden heat that you have to add to make it go through that phase change. You can notice right here in every single substance that they illustrate, mercury, water, diethyl ether, and butane, that the hidden heat or the latent heat of vaporization is much larger than the heat of fusion. And if you remember back a little while ago, we talked about how the solid and liquid phases were called the condensed phases, and then the gaseous phase was kind of off by itself. And this is one of the main reasons, because it takes so much more energy to go from that condensed liquid phase to the gaseous phase than it does to simply go between the two condensed phases, the solid and the liquid. So there are energy changes associated with this change of state, and the heat added to the system at the melting and boiling point goes into pulling the molecules further apart from each other. The temperature of the substance does not rise or change during this phase change, but the heat must be added in order for it to change phase. So if we took this graph right here of temperature versus the amount of heat added, notice heat is on the horizontal axis, heat energy. Temperature is on the vertical axis. You notice if we're at negative 25 degrees Celsius for water, it's at ice. At 0, now all of a sudden we say, oh, it's going to change from ice to liquid water. And it does, but you have to add some heat right here to make that happen. This red line right here is that latent or hidden heat to make it go from solid to liquid. Remember, it's the latent heat of fusion right here. Then we heat it up to 100 degrees Celsius, and at sea level, it'll start to vaporize. It'll go from a liquid to a gas. But we have to add some heat to it right here, and notice how much more heat we have to add to it right here, because it's going from a liquid to a gas. And remember, this is called the hidden heat of vaporization, or sometimes called the latent heat of vaporization. Now, if we went the opposite direction, from top down, we'd actually call these heats, this red one right here, and this red one right here, different names. Okay, we call this the heat of condensation. And then down here, this would still be called the heat of fusion because we'd be taking it going from a liquid to a solid and fusing it together. That's another way to think of that. Okay, another consequence of intermolecular forces is something called vapor pressure. At any temperature, some of the molecules in a liquid have enough energy to escape. As the temperature rises, the fraction of the molecules that have enough energy to escape increases. And so this is a simple concept that you've actually all seen but never really maybe thought of this way. If you take a glass of water and set it on the countertop and leave it there for a week, what happens to it? Well, eventually the water will all evaporate, right? Well, the reason that it evaporates is because some of the molecules in the liquid have enough energy to escape and become a gas. Now, it's not at its boiling temperature because it's just sitting out at room temperature, but some of them have enough energy to escape. And this, when it's measured in a closed container, is known as the vapor pressure of the liquid. Sometimes I like to say this backwards and say it the pressure of the vapor of a liquid. Because if we took that glass of water that you set on the countertop and actually put a cover on it, and then inside of the cover we put some device to measure the pressure inside of there, we could measure how much air pressure, I call it air now because it's got nitrogen, oxygen, and water vapor in it. If we measured that pressure only from the water molecules that have evaporated, we would say it's the pressure of that water vapor that's inside of that cup. Well, as the temperature rises, more of that water starts to evaporate because the fraction of molecules that have enough energy to escape increases. And you can look at this graphically. You can see at a lower temperature, a lot of the particles stay in this blue graph right here, and these over here would be in the liquid phase. And then you see at a higher temperature, the graph starts to go a little bit lower on the hillside, and you get more that have this minimum amount of kinetic energy that is needed to escape from the liquid and go to the gaseous phase. So the higher the temperature, the higher the vapor pressure. As more molecules escape the liquid, the pressure they exert increases. The liquid and vapor reach a state of dynamic equilibrium. Liquid molecules evaporate and vapor molecules condense at the same rate. And you can see right here inside of this bubble container that some of these gaseous molecules become liquids and some of these liquid molecules become gaseous molecules. And they do that at exactly the same rate. And we can measure the pressure exerted by these vapor particles, gaseous particles right here, by measuring the distance right here that the mercury, or the substance we're using to measure the push of the gas against it, and then that will tell us what is the equilibrium vapor pressure, or the pressure exerted by the vapor of that liquid. The boiling point of a liquid is the temperature at which the vapor pressure is equal to the atmospheric pressure. The normal boiling point is the temperature at which its vapor pressure is 760 torr. If you remember back to our gas laws chapter, 760 torr is standard atmospheric pressure. That's what atmospheric pressure usually is at sea level. And if you look at this graph, it looks kind of simple to start with, but it actually has a lot of deep meaning. Here's temperature on the horizontal axis. Here's vapor pressure in torr on the vertical axis. Now follow water. You'll notice as temperature increases, vapor pressure starts to increase. In other words, the water in its liquid phase is starting to have more of it evaporate and become vapor. And notice when we reach 760 torr right here, normal atmospheric pressure, the temperature is 100 degrees Celsius. Hey, what happens to water usually at 100 degrees Celsius? Well, it boils, right? Yeah, as long as we've added that latent or hidden heat of vaporization, it will boil. And this is technically what the definition of boiling is. Boiling is not 100 degrees Celsius, as I've told you before, for water. Boiling is when the vapor pressure of the liquid is equal to the atmospheric pressure. And so if we're at standard atmospheric pressure, then we get what's called the standard boiling point, or 100 degrees Celsius. A complex thing to think about. And we'll do a couple demonstrations like this as well, because you can actually change the atmospheric pressure by going up high on a mountain or putting a substance inside of a vacuum chamber. And then when you do that, you of course change the boiling point of that substance. Well, it's handy to diagram all the phase changes of a substance in one place. And the diagram that scientists use lots of times to do this is called a phase diagram. They display the state of a substance at various pressures and temperatures and the places where equilibria will exist between the phases. And you can see right here that a phase diagram exists of the solid, liquid, and gaseous phases of a substance. And you can see that it's pressure on the vertical axis and then temperature on the horizontal axis. And you can see that there's several lines and several points that are of very strong interest to us. These lines right here, like A to D, represent the solid to liquid phase change, sometimes called melting when it goes from solid to liquid, or called freezing when it goes from liquid to solid. Or when we go from liquid to gas, it's known as vaporization, or gas to liquid, it's known as condensation. Or down here, the AC line, you can see that's the sublimation deposition line right there. And you can figure out, knowing what the temperature is and what the pressure is, what phase of matter the substance will be in, or what it will change through, depending on how the pressure and temperature of something will change. AB line is the liquid-vapor interface. It starts at a place called the triple point, a point at which all three states are in equilibrium. Notice right here, the substance is a solid, liquid, and gas all at the same time. It ends at the critical point, B. Above this critical temperature and critical pressure, the liquid and vapor are indistinguishable from one another. Indistinguishable from one another. Above this, you'll usually see this AB line become vertical, straight vertical right here. It's indistinguishable between gas and liquid. It's actually both. Strange concept. Each point along this line is the boiling point of the substance at that pressure. Remember how we said boiling could change depending on what the atmospheric pressure is? Well, here you go. The AD line is the interface between the liquid and the solid. The melting point at each pressure can be found along this line. You can notice that melting and freezing is also slightly affected by pressure. Below A, the substance cannot exist in the liquid state. It only exists as a solid or a gas. Along the AC line, the solid and gas phases are in equilibrium. The sublimation point at each pressure is along this line, or you could call it the deposition. Note the high critical temperature and critical pressure. These are due to the strong van der Waals forces between the water molecules, and the slope of the solid-liquid line is negative. This means that as the pressure is increased at a temperature just below the melting point, water goes from a solid to a liquid. And this can tell you actually, since it has a negative slope, that the solid substance will be less dense than the liquid substance. A lot of people get used to looking at the phase diagram of water and they think that all phase diagrams should look like this. Actually, water is one of the few substances that has a negatively sloped solid-liquid interface line. It's because there aren't many things where the solid is less dense than the liquid. Usually the solid is more dense than the liquid. You'll notice that the graph is not really drawn to scale at all. 4.58 torr in 1 atmosphere should really have like a mile between them right here. And then we jump from 1 atmosphere to 218 atmospheres. I mean, that it's not really to scale at all. Here's the phase diagram for carbon dioxide. Carbon dioxide cannot exist in the liquid state at pressures below 5.11 atmospheres. CO2 sublimes at normal pressures. And of course, since we live on Earth where normal atmospheric pressure is about 1 atmosphere, we usually see carbon dioxide in either the solid or the gaseous phase. 1 atmosphere right here goes from solid to gas. We call that sublimation. And that's why we call solid carbon dioxide dry ice, because it doesn't go through a liquid phase change. Can you have carbon dioxide liquid? Sure. Just put it above 5.11 atmospheres and then you can move into the carbon dioxide liquid phase as long as it's above negative 56 degrees Celsius. And then, of course, once you get it up in this temperature range, then it becomes a gas once again. Below critical temperature and critical pressure CO2 makes supercritical CO2 a good solvent for extracting nonpolar substances such as caffeine. As a matter of fact, they use this to make decaffeinated coffee. You can see right here the slope of this line between the solid and the liquid has a positive slope. Meaning that solid carbon dioxide is more dense than liquid carbon dioxide. We're now going to change gears just a little bit and finish up this chapter kind of quickly with just a little overview of solids. Okay, mostly we've been focusing on the phase changes now between solid, liquids, and gases, and we explored some of the intermolecular forces that hold things together in the gaseous, liquid, and solid phase. But now we're going to focus more solely just on what holds solids together and what shapes they have. We can think of solids as falling into two groups. Crystalline solids, these are particles that are a highly ordered arrangement, and amorphous solids. They have no particular order or arrangement of particles. Looking back at this one, this is crystalline SO2. You can see that it has a very ordered arrangement, nice little hexagon arrangement between the SO2s. And then you can look at this one right here where it's all different. I mean, it still makes some shapes, but there's different shapes all around. Amorphous SO2 is kind of like a liquid that's just frozen in place. You've seen a lot of amorphous SO2. Some people call this glass. In ionic crystals, ions pack themselves so as to maximize the attraction and minimize the repulsion between ions. You can look back here and you can see how they'll arrange themselves in what's called the close packed layering. And you can see if they're just one type of sphere together. If there's two different kinds, notice how they're kind of set at different intervals. And here you can see there's actually three different kind of intervals right here when there's three things stuck together. Because of the order in a crystal, we can focus on the repeating pattern of the arrangement. It's called the unit cell. And so the unit cell is actually like a box or a cube, where at each corner of the cube we have a ion or a particle that's stuck together. And you can see there are three examples right here of different unit cells: primitive cubic, body-centered cubic, there's a body in the middle, and face-centered cubic, where the faces of particles are on each side of the cube. There are several different types of basic arrangements in crystals, such as the ones shown above. And you can see that you could actually add up how many atoms there are in a particular primitive body or face-centered cubic structure, because each one has a certain part of a particle in there. You don't need to memorize that. We can determine the empirical formula of an ionic solid by determining how many ions of each element fall within the unit cell. And you can see right here how many of each particle or fraction are in a particular unit cell. And here's a quick question about what are the empirical formulas for these substances. Greens are chlorine, grays are cesium, and you can see right here we have one type of unit cell. Here's another type, here's yet a third type. So you can see that the cesium is CsCl, zinc is ZnS, and the calcium one is CaF2. So here's a summary of types of bonding in crystalline solids. So molecular types are atoms or molecules that are stuck together. They're held together by London dispersion forces, dipole-dipole forces, or hydrogen bonds. They're usually fairly soft. And you should memorize some of these properties and some examples of these molecularly stuck together things. Next ones are covalent networks. Covalent networks are very unique. They're atoms connected by networks of covalent bonds. They're very hard. They have very high melting points, and they're often poor thermal and electrical conductors. Diamond, quartz, SiO2, pure carbon are good examples of that. These are many times confused with molecular substances. But if you just remember silicon and carbon, you generally get the covalent network ones right. Ionic substances, positive and negative attractions, hard, brittle, high melting points because they're held together by ionic bonds. And then metallic things are held together by metallic bonds. And they can have a high or low melting point depending on what they are. They're usually good electrical conductors, they're malleable and ductile, and examples of these are copper, iron, aluminum, platinum. Here's a couple of examples of covalent network and molecular solids. Diamonds are an excellent example of a covalent network solid in which atoms are covalently bonded to each other. They tend to be hard, having a high melting point. And then graphite is an example of a molecular solid in which atoms are held together with van der Waals forces. They tend to be softer and have low melting points. And you can see right here how there's like a nice straight structure or a flat plane of carbon atoms connected with these van der Waals forces, that's what these red ones are, to another plane of carbon atoms, another plane of carbon atoms right here. And I don't know if you know this or not, but pencils are made of graphite. And when you draw, you're actually like rubbing off various layers like this of these graphite layers. And the reason you can break them off fairly easily and take your pencil and put some of your pencil lead on your paper is because these forces right here, these van der Waals forces, aren't super strong. That's why you can't write with a diamond, because they're held together a lot. This is incorrect English. A lot more strongly than what these guys are right here, because these only have little van der Waals forces holding them together, which makes them good for pencil lead. Metallic solids, they're not covalently bonded, but the attraction between atoms are too strong to be van der Waals forces. In metals, valence electrons are delocalized throughout the solid and shared by everyone. And so you can see that they have these fixed patterns or arrangements like this, and the electrons are just shared between all of the nuclei. This delocalization of the electrons right here, you can see that they're all over, allows them to be good electrical conductors. And since the electrons are kind of free to be squished around, it makes metals fairly malleable, means they can be mushed into shapes, and ductile, means they can be drawn into wires. And that's why we use metals as good conductors and wires to conduct electricity. That does the overview of Chapter 11, Intermolecular Forces, Liquids and Solids.